Hello, everyone. I wanted to record a quick preamble to Lecture 13. While researching for Lecture 13, I realized that Calabi-Yaus are even more vast than I previously thought, which I already thought they were pretty vast. And they are kind of on the border or even were outside of the border of what I knew about complex differential geometry before I started writing lecture 13. So I felt that it's important to preface this lecture by saying that this is on the border of what I know and to not give an air of expertise in a subject that I don't have expertise in. This is my first dive into Calabi-Yaus, and it's my best synthesis of what I learned so far. I hope you take it as that, and there will be limitations because of that, but I'm really thinking of this now as version 1 of this lecture, and hopefully with feedback, which you are free to leave below, I'll improve this lecture, maybe just in the written version. I don't know if I'll re-record this video, but we'll iterate on this, and hopefully a future version of this lecture is going to feel more complete and exhaustive as a review of Calabi-Yaus in 10 pages. So without further ado, I still hope you enjoy this lecture, find it helpful, and I still hope it achieves its central goal, which is to motivate why we care about Calabi-Yau manifolds, why they're so interesting, and why both physicists and mathematicians find them so important. So yeah, let's get on to the main segment. Hello, and welcome back to Complex Differential Geometry, where we're on our final lecture that's going to be on Calabi-Yau manifolds. We just finished Kähler manifolds in lecture 11, and we did Hodge symmetries and Hodge structure in lecture 12. So we're going to get into Calabi-Yau manifolds now after a brief recap of what we did last time, as we usually do, and this is going to be our final recap. So what did we do last time? We looked at the Hodge theorem, and in order to do the Hodge theorem, we set up all this Hodge machinery. I'm just going to call all of it Hodge machinery in one overall category. So we have things like volume forms, both real and complex volume forms. We had the Hodge star operator. We had Hodge inner products. And then we use that to define the Laplacian operators, which were delta D, delta partial, and delta partial bar. We use that to define harmonic forms. And once we had all of that, we were able to state Hodge theorem, which had three substatements. One, that the harmonic forms are finite, forms are finite dimensional as a set. Two, that the cohomology groups HPQ partial of M is isomorphic to the harmonic forms HPQ partial of M. So there's a unique harmonic representative for each cohomology group. And then number three, the Hodge decomposition. The decomposition, let me write it like this. There was a harmonic part plus the d of omega k minus 1 plus d dagger of omega k plus 1. Something like that, just as a very brief summary. And then we looked at the Kähler identities, which led to enhanced Hodge theorem. This is different from the complex version of the Hodge theorem, and here we were able to split the K grading in and descended into the PQ grading, if you remember, because we found that delta D is equal to 2 into delta partial is equal to 2 into delta partial bar, so that they were all proportional to each other. So if something is d-harmonic, then it's partial harmonic, it's partial bar harmonic. So then we looked at properties, we looked at Hodge symmetries, or symmetries in the Hodge numbers. We looked at the property of the Betti numbers, the odd Betti numbers being even, and we looked at Lefschetz decomposition, which was this decomposition involving the primitive cohomology classes and the Lefschetz operators L, lambda, and H. Well, H was just there to complete the SL2C representation, because we also saw that these formed a representation of SL2C. All right, so that's what we did last time. This was all the stuff we did in lecture 12 in a very summarized fashion. So now we're going to talk about Calabi-Yaus. And specifically, let me start off by talking about our agenda for today, what we're going to cover. We're first going to talk a little bit about the history of how Calabi-Yaus came into being. We're going to cover Calabi's conjecture, and Yau's proof. We're not going to get into what Yau's proof was, but we're going to just get into it in a surface level. It will frame how we're going to define definition. Our definition is going to be three-tiered. So we're going to have weak Calabi-Yaus, strong Calabi-Yaus, and strict Calabi-Yaus. And I originally had 5 different definitions, and I looked into how they were related to each other. It became really complicated, so I ended up deciding that it would be simpler and more understandable if I just sorted them into 3 different tiers, and so we got these 3. This is the definition that's most commonly used in string theory and in geometry, but we will look at each and every one of them. Even the weakest Calabi-Yaus have the defining property that we always most famously associate with Calabi-Yaus. So after we're done with that, we will look at some of the topological properties, get the easy ones out of the way, just like we did with Kähler manifolds. We're then going to talk about these fascinating spaces called moduli spaces and the moduli spaces of Calabi-Yaus specifically. There's a lot of interesting structure to be had there. We're going to look at the enhanced Hodge symmetries, the ones that go above and beyond the symmetries of the Kähler manifold that is underlying it, right? And then lastly, we have to talk a little bit about why Calabi-Yaus, specifically three-dimensional Calabi-Yaus, are important to string theory. No discussion of Calabi-Yaus is complete without a discussion of string theory, but let me give myself a little bit more space here. But because we're doing math here, we have to be talking about why Calabi-Yaus are important not in string theory. And that will do it for our lecture today. So let's start talking about the history of Calabi-Yaus. Right, so let's move on to the next page. A little bit about the history. We're going to be very accursory with the history. Just the mathematical insight into what was happening. So basically, what we started off with is this big problem in Riemannian geometry called the prescribed Ricci curvature problem. What was this problem? This problem stated that if I given, we have an M, which is a smooth manifold, and I give you R, which is a symmetric two form. Can you give me a G, a Riemannian metric, a Riemannian class metric, for which Rich of G will give me a row, which is, this would be the Ricci form, as we talked about I think in lecture 11. So this is the Ricci form that is equal to R, right? This is the prescribed Ricci curvature problem. In general, as far as I am aware, it is unsolved. But in 1954, mathematician Eugenio Calabi, one half of Calabi-Yau, conjectured. Now, the conjecture is very long. I actually have the original text in the lecture notes, but I'm just going to read it out and I'm going to write down the important details. So, Calabi's conjecture is that we say that let M be a closed m-dimensional complex manifold. Assume that M admits at least one Kähler metric. We'll call that K. So that's our Kähler metric. Admitting a Kähler metric means that you're a Kähler manifold. So Kähler metric. This implies that we're going to have an omega. This is our Kähler form. The conjecture stipulates that its associated exterior form is omega, which is equal to I k alpha beta bar dz alpha wedge dz bar beta bar. Of course, I am translating all of this into our own notation so that it's easier to understand, but this would be our Kähler form, a closed exterior 2 form, and so this would produce a cohomology class. We call it square brackets omega. This is an element of the second de Rham cohomology class. Because remember, the Kähler form is in fact real even though it's in terms of complex numbers, because it has that property where it's equal to its conjugate. So this is called the principal cohomology class of the metric, in this case K. Then we will have R, which is our name for the Ricci curvature tensor field. Ricci curvature tensor field. And this will give us a Ricci form rho equals I R alpha beta bar dz alpha wedge dz beta bar, which is another 2 form. It's closed, and its cohomology class, as we know already, is 2 pi c1 of Tm, where Tm is the tangent bundle. M being the manifold that we're on, and this is the first Chern class. We're all familiar with this by now. We just replaced E with Tm. So then what is the conjecture? The conjecture is that given any real closed infinitely differentiable 1-1 form, let's call it sigma, which is cohomologous. So that's saying that if the cohomology class is equal to 2 pi c1 tm, then we must be able to produce a Kähler metric K element of omega. Oh, I haven't introduced omega yet. I'll introduce it in a second, such that K gives us a rho which is equal to sigma, a Ricci form. So that's the conjecture. So omega is the space of infinitely differentiable Kähler metrics. This is not the omega that we've been using so far. This is an omega that Calabi is using by himself. This is the conjecture, and it was proven by Yau's proof. Now, Yau proved this in 1978, and we won't get into the details of the proof, but it suffices us to say that what Yau did is he took a specific partial differential equation, which, let me write it out right here. In terms of differential forms, it looked like this, where we have the Kähler form, and we have phi, which is the Kähler potential. Now, this was a nonlinear partial differential equation, and Yau's contribution here is that he came up with a system of a priori estimates for a simpler PDE where f is equal to 0 in this equation, and then he continuously deformed the equation to be a solution for the full PDE. And the way the proof is structured, if you have a solution for the easier PDE, then the continuous deformation ensures that it stays a solution when you deform the equation to the more difficult PDE. And so that's how Yau proved Calabi's conjecture, and that ended up in Yau's theorem. I'm not going to rewrite everything because, in fact, Yau's theorem is just Calabi's conjecture, and it says that if given any real closed infinitely differentiable 1-1 form, that this is possible, that you can find a Kähler metric, a unique Kähler metric, such that this is true. So that's Yau's theorem, and Yau tells us that such a unique Kähler metric is always possible. And you might think that once we choose, so choice of Kähler metric gives us a Calabi-Yau. Now, you might call this a Calabi-Yau manifold, but this isn't usually what we call a Calabi-Yau, because rho could still be anything. So if, let's say, we choose any sigma, so then rho could be whatever sigma we chose as our symmetric 2 form. When the point at which we get a Calabi-Yau, and here's where we define our first version of a Calabi-Yau, a weak Calabi-Yau, it's what I'm calling it, a weak Calabi-Yau manifold. I'm going to be calling Calabi-Yau manifolds Calabi-Yaus because it's common to call them that, is one for which C1 of Tm is equal to 0. It has vanishing first Chern class. Why? Because this implies, according to Yau's theorem, that rho is equal to 0. And this is where we get the notion that a Calabi-Yaus are Ricci-flat Kähler manifolds. And that's basically it. This is the most famously associated property with the Calabi-Yau, but it doesn't go both ways. Rho equals 0 doesn't always imply that C1 of Tm is 0. So the first Chern class vanishing is a strictly stronger condition than Ricci flatness. And this is, by the way, I forgot to mention, this also means that Rich of the metric K will be equal to 0 as well. This is why we call it Ricci flat. So why is that? Because rho being 0, rho equals 0 constrains the real cohomology class H2M real, but the true first Chern class is a function of the integral cohomology class. If you remember, we were talking about that nuance when we introduced the Chern class. It's actually this. So there are situations in which rho equals 0 can cause the real cohomology class to be 0 without causing the integer cohomology class to be 0. And those situations is what means that this Ricci flatness is not the same thing as the vanishing first Chern class. Oh yes, here what I meant is C1 of Tm is this actually, right? So that's what I meant, is that the integer cohomology class is this guy in the more true sense, in the more accurate sense. Yeah, so this is a weak Calabi-Yau manifold, and this fact where we set these two to zeros. So we had Yau's theorem, which told us that for any symmetric two-form sigma, we could get a Riemannian metric G, or K in this case, which because it's also a Kähler metric, which had this sigma as its Ricci form. And so we could get any Ricci curvature we wanted. That's what Yau's theorem told us. Now what we did is we set that curvature, we set sigma to 0. And that's what gave us a real Calabi-Yau manifold. And this result with the zeros is called aptly Calabi-Yau theorem. It's a corollary of Yau's theorem. It's just a special case of Yau's theorem for when sigma is equal to 0. So this leads us to an important consequence of the weak Calabi-Yau manifold. The weak Calabi-Yau manifold has a specific holonomy, and in specific, it's the restricted holonomy group that we're talking about. For a weak Calabi-Yau, the restricted holonomy group is a subset of SUM. Usually you call this SUN, but since I'm using M as the dimension of the manifold, SUM. So this is an important restriction on Calabi-Yau manifolds. If you remember, the holonomy group of a general Kähler manifold has to be inside UM, but for a Calabi-Yau, this gets even further restricted to be inside SUM. So this is a result of a theorem, Ambrose-Singer theorem. What is Ambrose-Singer theorem? Well, Ambrose-Singer theorem gives us a connection between the Riemann curvature and the holonomy of a manifold. So what does it say? If we have a Riemannian manifold, MG, with Levi-Civita connection that is guaranteed with the Riemann, the fundamental theorem of Riemannian geometry, so we have a Levi-Civita connection, then what we get is that the Lie algebra of Hall 0 Pm for a point P is given by P gamma inverse after RQXY after P gamma, which is an element of the endomorphisms on TPM. So let me unpack that. It's given by the linear span of all these elements. So what does this mean? P gamma is the parallel transport operator along the curve gamma. Q is any point that is connected to P with a piecewise smooth curve. So a piecewise smooth curve being this is smooth, this is one piece, this is smooth, this is smooth. That's a piecewise smooth curve. So any point, Q is any point that is connected to P via piecewise smooth curve. And RQXY is the Riemann curvature operator centered at Q. And obviously, P gamma inverse is the inverse of the parallel transport operator. And this is the set of endomorphisms on the tangent space of M at P, which is the matrices that are over that vector space. That is the linear maps on that vector space that go from the vector space to the vector space. So the vector space being TPM. So these are a bunch of endomorphisms. So these are a bunch of linear maps. These linear maps, their span, if we use them as a basis to span all of some space, then that Lie algebra is the Lie algebra of Hall P M0. So what is this? This is the restricted holonomy group of M at P. So holonomy, remember, means that we have this parallel transport operator go around in a loop, and we look at what happens to vectors around in that loop. And the restricted means this is a term in group theory where, remember that Lie groups are manifolds. So let's say that I have a manifold that has a lot of different pieces. We didn't really look at manifolds that look like this. It was kind of implied. But manifolds can come in several pieces. They don't have to all be attached to each other. So if we have this sort of shape, then let's say that this part of the manifold has the identity element of the group in it. So this would be called the component continuously connected to the identity. And if this was a group in and of itself, then that would be called the restricted group. Maybe you've heard of, let's say, the restricted Lorentz group. That's the same idea there. It's the part of the Lorentz group that is connected to the identity. The Lorentz group itself comes in 4 pieces. So, okay. So that's the restricted holonomy group of M and P. Of course, you'd have to take the equivalence class of curves, modulo their base point, and then you would get, you would go from Hol P0M to something called Hol 0M. We talked about this briefly before, but it's been a while, so I'm rephrasing it. This is the holonomy group over the restricted holonomy group over the entire manifold, as opposed to a specific base point P. So yeah, we're just removing that dependence on the specific base point P. Okay, so that's what it says. So what can we say about this? What we can say is that we know that for a Calabi-Yau, the Ricci curvature is 0, right? So, or let's say that Rich of K is equal to 0. This implies that the Riemann curvature, and therefore the Riemann curvature operator, is traceless, because the Ricci curvature is the trace of the Riemann curvature. Traceless? Traceless matrices are, or traceless operators are what form RQXY. That means that it's an element of the Lie algebra, little SU. I'm trying to do a little fractal font here. So that's little SUM, the Lie algebra, but we also know that P gamma inverse and P gamma do not affect the group. Yeah, they keep it invariant. So this means that this is also an element of this Lie algebra. And if this is the Lie algebra, if this is the Lie algebra of the restricted holonomy group, then holonomy group, once you use that exponential map, will give us, this implies that Hol P0M is equal to SUM, which is the Lie group that is connected, or that is corresponding to that Lie algebra. And then you can modulo the base point, and then you get the holonomy group of the entire manifold. There are some subtleties there, but I'm trying to get over the main conceptual points in this argument. So from here, we know that, as we said before, that Hol 0M of a weak Calabi-Yau manifold, so this is a weak Calabi-Yau, is a subset of SUM. Right, so shouldn't have written equal to over here. This should be subset of. Right, so this is a key fact. This is important in choosing which definition to use for a Calabi-Yau. That's why we're spending some time in understanding this property. And it's going to change as we get up into like more strict definitions of a Calabi-Yau. So that was weak Calabi-Yaus. Now let's look at strong Calabi-Yaus. In order to define a strong Calabi-Yau, we're going to need to know what a canonical bundle is. Canonical bundle? It has a fancy name, but it's actually pretty simple. The canonical bundle is, for a complex m-dimensional manifold, is just Km, that's what it's called. It's equal to lambda to the m of T star 1, 0 of m. This is called the canonical bundle. And you can also, by the way, have something called the anti-canonical bundle, which is just lambda to the m T star 0, 1 m. This is the bundle of holomorphic m-forms. Holomorphic holomorphic M-forms, kind of running out of space over there, and similarly anti-holomorphic M-forms. So one last thing we'll need is, what does it mean for a canonical bundle to be trivial? A canonical bundle is trivial if Km is isomorphic to M cross C. So if this is true, then we say that the canonical bundle is trivial. If this is true for our manifold, for our weak Calabi-Yau manifold, then it gets upgraded to a strong Calabi-Yau manifold. What do I mean by that? Well, we have the holomorphic M-forms. If the holomorphic M-forms are isomorphic to, this is essentially what we would call the trivial line bundle, also known as curly OM, then if the canonical bundle is isomorphic to the trivial line bundle, then we get a strong Calabi-Yau manifold. Now, this is as opposed to a weak Calabi-Yau manifold, a weak CY. For a weak CY, we have the notion that C1 of Km is equal to 0 because C1 of Tm is equal to 0, or Tm if you'd prefer, is equal to 0, which, Km is a power of Tm. So this means that Km admits a flat connection. A flat connection meaning one with 0 curvature, but that doesn't mean that Km is isomorphic to the trivial line bundle. In order for it to be isomorphic to the trivial line bundle, we would require the existence of a non-zero or a nowhere zero holomorphic section. In other words, we need there to exist an omega, which is an element of omega M0, such that omega p is not equal to 0 for all p element of M, right? And this is generally called, this M0 form, this element of the canonical bundle, is usually called a holomorphic volume form. It's a top-dimensional form. Well, it's a top-dimensional holomorphic form, and if the canonical bundle admits such a form, then the bundle will be trivial. And so we are also ensured the existence of this volume form, which turns out to be pretty useful. But it also means that we upgrade our restricted holonomy to the full holonomy. So the full holonomy is now SU, a subset of SUM, which is pretty nice. And so that is the definition for the strong Calabi-Yau, and we have one left, which is the strict Calabi-Yau. This one is pretty simple. The extra properties are always that it must be simply connected. This simplifies a lot of things, as the name suggests. And also, secondly, sometimes that it is irreducible. This means that the manifold's universal cover, the cover that contains all other covers of the manifold, is not a product of two or more lower dimensional non-trivial manifolds. And sometimes we stipulate for the strictest conditions of a Calabi-Yau, we want them to be irreducible. And this means that we get this really nice property that HP0 is equal to 0. These are the Hodge numbers for all P between 0 and M, strictly. And this, we'll get more into this when we talk about Hodge symmetries, but for strict Calabi-Yaus, we get this nice property, and this is often useful in string theory contexts, and just generally desirable if you want a very simple Calabi-Yau. The other thing that it does is that it means that our holonomy group is no longer just a subset of SUM, it must be SUM. And so this is the strictest version of the Calabi-Yau, And the next thing we're going to look at is, now that we're done defining all three tiers of a Calabi-Yau, we will now look at some of the topological properties of a Calabi-Yau manifold. So let's flip over the page and get right into topological properties. Topological properties. I'm going to start with number 0 because this has already been established. C1 of Tm, the first Chern class of the tangent bundle, is equal to 0. So this is what we defined a Calabi-Yau using, vanishing first Chern class. So let's get to some of the newer properties. For the Calabi-Yau, there are restrictions on the higher Chern numbers. And so why is this? This is given by something called, I don't know if I'm going to pronounce this right, Herzebruck-Riemann-Roche theorem, or Roch theorem. I'm not exactly sure. So what does this say? It says that for any theorem, for any complex algebraic variety. So what's an algebraic variety? An algebraic variety is, for our purposes, it's a kind of manifold that can be described by a polynomial equation. So it's a subset, it's a stricter version of the conditions on what causes a geometric space to be manifold. So for any complex algebraic variety, the Euler characteristic, if you remember the Euler characteristic from topology, characteristic is given by chi, which we usually call the Euler characteristic of m comma e, is equal to the integral over m of the, I'm going to explain what this is. This is ch of e times td of m. This is something called the Chern character. Chern character. And this is something called the Todd class. We don't really need to know too much about what the Todd class is, other than it's a polynomial involving Chern classes. And if we take M to be, let me write it here, M to be a Calabi-Yau manifold, and if we take E to be the trivial line bundle, then what we get is chi of Cy OM is equal to an integral over the entire Calabi-Yau of the Chern characteristic of OM and times the Todd class of the Calabi-Yau. Now, it turns out that the Chern character of a trivial line bundle is always 1. So we can take this out of the equation. All we have left is a polynomial in the Chern classes. And we know that C1 of OM is, you could also think of this as the canonical bundle, being isomorphic to OM. We know that this is equal to 0 for our Calabi-Yau, right? And this means that we get some constraints on the higher order Chern classes. So for example, for a three-dimensional Calabi-Yau, the Todd class, TD3 of the Calabi-Yau is equal to 1 over 24 C1 times C2, which these are the Chern classes. And so since C1 is equal to 0, we get that this is equal to 0, which means that chi of Cy of OM is equal to, or Cy3 of OM is equal to the integral of 0, which is 0. And similarly, because the Todd classes of odd dimensional manifolds, it always involves a C1, you will find that all of them give you 0. And this leads to the interesting conclusion that odd dimensional Calabi-Yaus have chi equals 0. So that is the first property. And so next we're going to look at something called number 2, Bogomolov theorem. And this tells us that any Calabi-Yau admits a finite Étalé cover. A finite Étalé cover is it's a covering space that is also a local biholomorphism, as in locally it is a map that is a holomorphism whose inverse is also a holomorphism that splits into a product of three, let's go to the next page, three manifolds. What are these manifolds? The product looks like this. A Calabi-Yau is isomorphic. Well, the cover, let's call it the cover of the Calabi-Yau is isomorphic to T times a product over xj times a product over yk. So what are these? T is a torus, a complex torus. Xj is a strict Calabi-Yau, so this is a weak Calabi-Yau. This is a strict Calabi-Yau, and this is something called a compact hyperkähler manifold, which sounds awesome, I have to say. But you could also call it a holomorphic symplectic manifold. And what that means is that it's a simply connected manifold that is also symplectic. So it has a symplectic form, and that symplectic form is holomorphic, and it's unique up to a scalar multiple. So that's what you call a compact hyperkähler manifold. And we know that any Étalé cover of a Calabi-Yau must be decomposable into a product of these three kinds of manifolds: a torus, a strict Calabi-Yau, and a compact hyperkähler manifold. So this is what we call Bovil-Bogomolov decomposition theorem. So that's property number 2. Let's talk about property number 3. So property number 3 is that there always existence of parallel spinor. This one is particularly important to string theory. We know that, well, what is a parallel spinor? So we have something called a spin bundle, which is just like a tensor bundle, except we have spinors instead of tensors. In the spin bundle, you can define something called a spin connection, which is a connection that connects spinor spaces. With respect to this spin connection, let's call it nabla S. If we find that nabla S of a spinor psi is equal to 0, then we say that that spinor is parallel. It's very much analogous to what we called parallel in terms of our previous connections. Now, for a Calabi-Yau, we know that because its holonomy group is SUM, that it always contains a parallel spinor. This is because of a fact that the spin bundle, let's call it S, is always isomorphic to a certain decomposition, Q equals to 0 to M of omega 0 Q tensor product with Km minus half. What's Km minus half? Well, previously I told you we were going to come back to the anti-canonical bundle. So this is an anti-canonical bundle, which is in some sense the dual bundle of the canonical bundle also. But this is defined by the fact that Km minus half producted with Km minus half is isomorphic to Km minus 1. So that's what this is. You could think of it as the square root of the anti-canonical bundle if you want to think about it that way. There's no square root operation going on here. The intuitive way to think about it is that it represents a twisted version of the anti-canonical bundle. And so because the canonical bundle is trivial, so the anti-canonical bundle is also trivial, and therefore its square root is also trivial. We don't have time to get into why that is, but all we know is that this is trivial. And so we're just left with this part. So this means that we will get a parallel spinner whenever we have a harmonic 0Q form. And this harmonic 0Q form, well, at least we will always have at least one of them if we take the Hod star of our holomorphic M form, which is, so Q here can be anywhere between 0 and M. So we get this one, and we can add on top of that a constant function. Let's call it 1, the constant function. That will be a 0, 0 form, which also still applies. So this is our 0M form. And so we always have at least 2 parallel spinners. And these parallel spinners, the existence of these parallel spinners is required in supersymmetry, which is why we need this property for string theory. So seems like we're at the end of the page. There is one more property. Let me center this. Number 4, smooth moduli spaces, or let's call it Bogomolov Tian Todorov theorem. Lots of theorems today. It says that something called the moduli space of a Calabi-Yau, and not a Kähler manifold, but specifically a Calabi-Yau, because of the Calabi-Yau condition of vanishing first turn class Ricci flatness, is locally isomorphic to a smooth manifold, and importantly, it's unobstructed, which is pretty rare. It's a pretty rare geometric property for a moduli space to be unobstructed, and Calabi-Yaus are one of those really nice spaces where the moduli space is unobstructed, and this is called a Kuranishi space, this unobstructed moduli space. But in order to fully understand what this theorem is trying to say, we're going to need to talk about moduli spaces, and specifically moduli spaces on Calabi-Yau manifolds. But before we get into that, let's talk about what a moduli space is. So let's say that I had a space. Well, let's visualize it as a space of 2D points, right? Let's say that that's x and that's y. Then any point here is a point x naught, y naught, right? Let's say that each of these points, let me pick a new color. Let's say that each of these points represents an object, in this case a geometrical object. So how can a point represent an object? Well, if there are a finite number of parameters that you could use in order to describe that object, then you could plot every combination of those parameters as a point in a space. That space is called a moduli space. Moduli space, singular modulus, a moduli space, and the moduli, so the parameters themselves, parameters are called moduli. Let's give an example here. Let's say that we wanted to parameterize the space of lines that are symmetric and go through the origin. So let me draw one of these in 2 dimensions, just to keep it simple. Then this is the x-axis, this is the y-axis. All you would need, okay, this isn't very symmetric, but just imagine that it's symmetric. What you would need is the angle to a reference direction, in this case, let's say the x-axis, and you would need the length or the half length, whichever one, because it's symmetric, it doesn't matter. We'll call that L, right? And L and theta become, in some sense, polar coordinates, but 2 coordinates that parameterize this line. Now, if we were to plot these L and theta in a space of their own, L, theta, right? And we could say this was theta naught, this is L naught, then this point might be L naught theta naught, right? And so that would be a point in our moduli space, and these would be the moduli of this specific geometrical object, which is a symmetric line that goes through the origin. You could see how this space could be like non-trivial. It could have holes where those specific parameter combinations don't work. Or you could have repetitions, right? For example, here we have an angle. That angle is eventually going to exceed 2 pi, and then we're going to start repeating. So there you could have more complicated shapes for these moduli spaces. They don't have to be continuous. They could have holes in them, etc., etc. So in general, moduli spaces can be quite interesting. They don't have to just be a 2D grid or a 3D grid or an ND grid. They can be quite interesting spaces. So this is what a moduli space is. We are interested in the moduli space where these points represent Calabi-Yaus. The problem with that, though, is that in general, like the general problem of classifying Calabi-Yaus is extremely non-trivial, probably unsolved. But in a certain regime, we can solve it, which is when we look at the parameters locally and we vary them one by one. So what do I mean by that? What it turns out to be is that the moduli space, let's call it curly M, of the Calabi-Yau locally approximately decomposes into a product of two moduli spaces. One of those is for the complex structure direct producted with another one, which is for the Kähler form. So in thinking two different deformations independently, we can come up with this moduli space, and we can look at these moduli spaces individually, which is what we're going to do. And the way we're going to do it is we're going to think of deformations to the metric, this Kähler metric K. And what that's going to do is it's going to split us into two different kinds of moduli. Ones which affect the Kähler form omega, and ones which affect the complex structure J. Right? So we're going to see how that works out. We're going to split it into two different types of deformations. We're going to map those deformations onto some parameters, and those parameters are going to be our moduli. So the important thing to remember is that we need to preserve under these deformations what it really means to be a Calabi-Yau, right? Because we don't want to deform our Calabi-Yau manifold in such a way that it no longer is a Calabi-Yau manifold. So what that means is that d omega equals 0, right? The Kähler form has to be closed so that it stays a Kähler manifold, which is a prerequisite to be a Calabi-Yau manifold. And 2, that it has to be Ricci flat. So the Ricci tensor of our metric has to be 0. So we have to make sure that when we are deforming the metric, we are not taking a Calabi-Yau and turning it into something that's not a Calabi-Yau. We're preserving its nature as a Calabi-Yau manifold. So that will reveal in a local sense what our moduli are. So the next thing that we're going to do is we're going to look at the deformations of this Kähler metric while preserving these conditions. So let's go to the next page. So what we're going to start with is we're going to have the Kähler metric K, and we're going to send it to K plus delta K. And here, an important thing to note is that we are doing everything locally. And locally, M is approximately, the manifold is approximately the same as TPM, the tangent space around that point. So we can then linearize a lot of the things that we're talking about. So let's say that we have the Ricci tensor of K is equal to 0, right? We'd like to preserve this condition. So what we're going to do is we're going to say that the Ricci tensor of k plus delta k is equal to 0, right? And what this will turn out to be is we can linearize this equation. And when we linearize this equation, what we get is the Ricci tensor of k plus delta k is approximately equal to the Ricci tensor of k. Because we're taking this infinitesimal deformation, we are allowed to say that, okay, well, we have the original Ricci tensor plus a little bit extra, which we're going to call delta rich, and this is going to be a function of delta k, and then we have some higher order terms, order of delta k squared. Right? And this gives us, so we already know that this is equal to 0, and since we're linearized, this is equal to 0, but that means that if this thing needs to be 0, then overall, that's a lot of things that need to be 0, but really what that means is that we get to say that this is 0, which is the important part. So this gives us something called, let me write it out. This is called the linearized Einstein equations. It's called that because it comes from general relativity, but the reason is that we are imposing Ricci flatness, which is something that comes from the vacuum conditions of general relativity as well. That, besides the point, the main point is that now we have this condition. And it seems like we're in the home stretch, but there's one caveat on top of this, which is that there are multiple deformations that will lead to the same underlying geometrical object, the same Calabi-Yau. It won't give you distinct Calabi-Yau manifolds. This is what we might call a redundancy in coordinates or redundancy in descriptions. Right? So there are two deformations that look different, but actually are the same deformation disguised in different coordinates. So we want to remove these redundancies. This is a process called gauge fixing. A gauge is a choice of such coordinates. The gauge that we're going to use is, I'm going to write it in coordinates, not in the coordinate free way, because that's how I have it written. So equals 0. This is our gauge condition. We call this a gauge condition. And it removes, just like in a system of equations where having an additional equation removes one of the variables, this is going to remove a spurious degree of freedom that allows us to have distinct deformations or distinct looking deformations that will actually end up giving us the same Calabi-Yau once we deform it. We don't want that. We want to go modulo indistinct Calabi-Yaus, right? So this is, a lot of the time, this gauge condition is called the harmonic gauge condition or the transverse gauge condition. And the reason for that is that if you add this onto the linearized Einstein equation, then you get something called, or that looks like this, delta L of small delta k is equal to 0, where this is called the, hope I can pronounce this correctly, Lichnerowicz. The way the Lichnerowicz operator acts is delta L of delta k is equal to, let's say, mn. This is the Riemann tensor, or the components of the Riemann tensor. So this is going to be, I'm translating it on the fly, m. So that's how the Lichnerowicz operator acts. And this condition just means that this is equal to 0. And this is called the Lichnerowicz equation. So which is equivalent to this. This is also the Lichnerowicz equation. This is just the expansion of it. And so what we get from this is, from the Lichnerowicz equation, is that this operator, delta L, commutes with J. And given that it commutes with the complex structure, that tells us something important. Usually when something commutes with the complex structure, what we get is that it preserves PQ decomposition. And this is where we come back to that idea that we had before. We will get two different types of independent deformations, delta K, J, K bar, and these are going to be 1-1 forms. And we'll have another version that will look like delta K, J, K, which are going to be 2-0 forms. And each of these will correspond to deformations of the Kähler form and deformations of the complex structure. And so now we're going to look at each of these one by one. We've perturbed the Kähler metric. We've preserved the Ricci flatness. We're going to look at delta omega and delta J separately. So now let's look at the deformations of the Kähler form. So let's start with the first kind. How are these related to omega? Well, we can think of it like this. If omega is equal to, this is the Kähler form, so we know that this is equal to K, J, K bar, dz, J, wedge, dz, bar, K bar, right? So then if we send this to omega plus delta omega, then we would get that this is equal to omega K, jk bar plus delta jk bar dz j wedge dz bar k bar. And we know that this first part gives us this, so that means this second part must be, oh, I wrote delta. That should be delta k. The delta k jk bar part must be this guy. So that's how we know that this is dependent on just the deformation. Okay, so what does that tell us? What that tells us is that, first of all, okay, so let me write it out. Delta omega is equal to I delta k j k bar dz j bar, oh sorry, dz j wedge dz bar k bar. So now that we have this established, we know that this must be a 1-1 form, and this is the only part that is allowed to affect omega. We can't take the 2-0 form part, which was the delta k jk part, because we know that omega is equal to, well, let me write it like this. Omega of xy is equal to the Riemannian metric g of j of xy. If we were to add a 2-0 component, then omega would no longer be a pure 1-1 form, which would inevitably change the complex structure, and we're not allowed to change the complex structure. Remember, we have to take the Kähler form and perturb it with keeping the complex structure constant. So the interesting thing is that we know that d omega has to be equal to 0, and we want to send it to omega prime, where we know that d omega prime has to also equal to 0 if it wants to remain a Kähler form. So that tells us that d of omega plus delta omega is equal to 0, which means that d omega plus d of delta omega is equal to 0, which means that since this is 0, we find out that delta omega 2 has to be a closed form. So delta omega is closed. But if we look at the Kähler class of omega, if we look at omega prime, we can look at these gauge transformations and see when they will result in not geometrically distinct new configurations, right? So that will happen when the Kähler class of omega prime is the same as the Kähler class of omega. So when does that happen is the same thing as asking when does omega plus delta omega, the cohomology class of that, equal to the cohomology class of omega. Well, that will happen whenever delta omega is an exact form, right? Because omega prime is homologous to omega if omega prime is equal to omega plus some exact form. That's the thing. So that both of these things, so delta omega, where do I write this? Delta omega is non-exact. It has to be non-exact for it to be not equivalent, right? That's what we said. This means that they're geometrically equivalent. So we then conclude that delta omega is non-exact, but if it's closed and it's non-exact, then it means that delta omega, or at least the cohomology class that includes it, must be an element of H11 partial. The 1-1 comes from the fact that we've already concluded that it must be a 1-1 form, so this is an element of that, and it's of the reals because omega is a real form, even though it has complex entries. So this tells us that, okay, well, what's the dimension of this? So this is the dimension of H11 partial is equal to H11. So the dimension of this space that of these deformations is there are H11 independent directions. So these can be parameterized by H11 different parameters. Or moduli, right? So these are the moduli, and so we call them TA, and A runs from, so let's say that A runs from 1 to H11. These are the Kähler moduli. So that's the Kähler moduli. Next, we're going to look at the other ones, the other perturbations that look like delta Kij, and those are going to end up affecting the complex structure. So let's do that. Complex structure. Moduli. So the first thing we're going to do is we're going to say that since we want K plus delta K Ij to be 0, since we want K plus delta K to be Hermitian, we might be tempted to say, okay, let's take delta Kij to be equal to 0 itself. Not only is this trivial, it would just reduce to Kij being equal to 0, which is the same thing as saying the original metric is Hermitian, which isn't saying that much. But also, it's not with respect to the old complex structure that we want it to be Hermitian, right? Because as we discussed in the section with the Kähler moduli, having a 2-0 form be added to our metric actually changes the complex structure, J, right? So what we need is for our perturbation for a new perturbed metric, K plus delta K, to be Hermitian with respect to a new complex structure, J plus delta J, right? That's what we really want. So delta Kij could be not equal to 0, and it would be fine. As long as we could redefine the complex coordinates in such a way as to restore the hermiticity of this new metric. So we will try to do just that. We will try to find out for what conditions delta Kij would give us a Hermitian metric and would preserve the property of the complex structure, which is that this J prime squared is equal to minus identity, right? But again, since we're working in this local space, what we can do is we can linearize this. So what happens when we linearize this? Well, first, before we linearize it, let's rewrite delta J as a linear order variation. So I'm going to write it like this. I'm going to explain this in a moment. So we got curly J of t dt of t equals 0 such that curly J of 0 is equal to our current J, the old J. And so what is J of t? J of t is a smooth curve in the moduli space, MCS. So the moduli space, if you remember, is a space where each of the points is a different complex structure. And so what J of t is a smooth curve where given a specific t, you are given, so this is that M CS, and J would then be, let me pick a nicer color here. This would be J of T, right? That's what we're saying. And so this is the linearized deformation. And so we needed this to linearize this condition right here. So we're going to do that now. If we substitute this definition into this, we go from j squared is equal to minus identity to substituting curly j of t after curly j of t, which is exactly what j squared is, right? J squared is j after j, is equal to minus identity. If we take the derivative of both of those sides, then we get d dt of j of t after j of t is equal to d dt of minus identity, but because that's a constant function, this goes to 0. And we need to use Leibniz rule for the other side. What does that give us? Well, first we get the derivative of the first one, dj of t dt at t equals 0. Well, that's what I forgot to write that here. Evaluated at t equals 0 after curly j of t plus curly j of t into the derivative dj of t dt at t equals 0. And on the other side, we get 0 because that derivative zeroed out. So this is exactly what we call delta j. Oh, and we need to evaluate this at t equals to 0 too. So that would give us, these would give us j of 0, right? So j of 0 would just be our original complex structure, and this would give us delta j. So then what we would get is delta j after j plus j after delta j is equal to 0, or in other words, delta j after j is equal to minus j after delta j, which means it anticommutes with j. So as long as delta j anticommutes with j, we know that this condition that we have over here will be true, or will be preserved for j prime. So that is the idea. So what do we do with that? Well, if it anticommutes with j, then what do we know? That applying delta j after j and applying delta j before j has a minus sign between it, right? So if I take something from T10, if I take something from the holomorphic tangent space, then what will happen is that this thing, the eigenvalue is plus I, right? But if I were to swap these things, and what j would do is it would introduce an I, right? So if delta j came first, what it's telling us that instead it would give us minus I. But that just means that we go to the anti-holomorphic tangent space. So what delta j does is it goes from the holomorphic tangent space to the anti-holomorphic tangent space if the input is from the holomorphic tangent space, and vice versa, of course. So we can define a specific vector field or tensor field. We'll call it mu, and we'll define it such that mu of v is equal to delta j of v whenever v is an element of T10M. So this is just a restriction. We're restricting, this is just delta j restricted to T10M. We're just allowing inputs from the holomorphic vector field. That's all mu is, and mu has a special name. The name of mu, I'm going to write it here. It's called the Kodaira-Spencer field. So I should say, what do we need mu for? I kind of started talking about this. We started defining mu. Didn't really explain what we're doing here. We're doing the same thing that we did with the Kähler moduli. We're trying to find a class, a Dolbeau cohomology class, and a Dolbeau cohomology group for the deformations to be equivalent to, so that we can figure out how many dimensions this space is supposed to be, so that we can tell how many complex structure moduli we're supposed to have, how many ways that we can deform this manifold so that the complex structure changes. So what we're doing right now is we're coming up with a way to count how many of those dimensions we have. So the next thing we're going to do is we're going to take mu and we're going to contract it in a specific way with the holomorphic M form that we have on our Calabi-Yau in order to get these 2-1 forms. So let's get into that. The first thing that we have to establish is that j is not yet known to be integrable. So when is it integrable? Now, there's a pretty long proof, and it's in the appendix of the notes if you want to look at it, but I'm just going to cut to the chase here for the sake of time. It turns out that this is when the Neon House tensor vanishes, right? And the Neon House tensor vanishing, if we linearize that, just like we've been linearizing everything else, we find that after some analysis, we get that partial bar of mu is equal to 0. And partial bar of mu equals to 0 is very close to what we got with d of delta omega being equal to 0 as well, right? With that being the case, we can have a very similar argument where instead of d, we have partial bar. Just replace which exterior derivative you're talking about, and you get the same idea. And with that, we get that the cohomology class of mu has to be an element of H1 M T10 M. And so the important thing here is that we're still trying to form this link between delta J and some cohomology group, right? So we need some isomorphisms between this cohomology class and the original one. Well, thankfully we do have one. Mu of V is equal to I over 2 delta J of V is an isomorphism. We're not going to prove that here, again, for the sake of time. But what that means is that we have that delta J is isomorphic to mu. So we have that first part of the link, but we're not out of the woods yet. We need one more, and as I said, we're going to have to contract this with the nowhere vanishing volume form. So maybe it's redundant to say nowhere vanishing volume form. Let me just say volume form. With the volume form, the holomorphic volume form. So we have one more step, which is to contract with our holomorphic volume form, which is chi, we're going to call it chi, is equal to, this is some new notation, iota. This, we usually don't use the Greek letter iota. It's coming in here as a special contraction. I'm going to get into exactly how it works in a second. So chi is going to be an m minus 1 form, because omega is an m form. By contracting with mu in this specific way, chi is equal to omega. I'm going to do some multi-index notation, I1 to IM, mu of k bar IM. So the IM is being eaten up by mu. You can think that they kind of destroy each other. That's the way I kind of think about it. So we're left with the basis 1 forms for dzi1 wedge dot 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 dzi m minus 1, because we've kind of annihilated these two, and we have to wedge that last one, dz bar k bar, right? And so this makes this chi, wondering where to write this. This is an m minus 1 form. I think I said 2-1 form last time. 2-1 form is for the Calabi-Yau with dimension 3. That's going to become important a little later when we talk about string theory. Yeah, in general, this is an m minus 1 form if you are talking about a Calabi-Yau M-fold, which is a fancy way of saying an m-dimensional Calabi-Yau. So this is our final form, the final differential form that we're going to use. And this is going to be an element of, or the cohomology class of this is going to be an element of H m minus 1 m partial bar C, right? So we need another isomorphism here. That isomorphism is exactly this guy over here. We always have that holomorphic M form. So this is our second isomorphism. But that means that we can write this. Delta J is isomorphic to mu, which is isomorphic to chi. So our moduli space is then the dimension of this space, which is H m minus 1. That's our Hodge number. So let me write it over here. It's the dimension. So that is how many complex structures. Sorry for moving the canvas around a little bit too much, but that Hodge number is the dimension for our moduli space. So we can say that dimension of MCS is equal to H m minus 1, which means that we're just going to call these chi A. We're going to call them in fact, let's call it chi B, because that B runs over more indices than A. So let's say that chi B are the complex structure moduli, and B runs from 1 to hm minus 1, 1. Or you might see this more often written as hn minus 1, 1, because most people use n as the number of dimensions. Anyway, it's immaterial. It's the same thing. So these are the complex structure moduli. So our space locally for a Calabi-Yau is split into these two, T A and chi B. That's our parameter space. One thing I forgot to talk about with the Kähler moduli is that we need the Kähler form to be positive definite. Remember, our metric has to be positive definite. That actually restricts the number of valid parameters that we have. And when we restrict mk to have only positive Kähler forms, we get something called the Kähler cone. We restrict to a subspace of that moduli space, and the result of that is called the Kähler cone. That's just one point of terminology and the subtlety of that whole part of the argumentation. But yeah, so at the end of the day, our total moduli space of the Calabi-Yau is approximately equal to, locally, MCS direct product with MK. And so this part, I actually wrote them the other way around. So this part is this one, and this part is this one. Maybe I'll do that with colors. So that is this one, and that is this one. So that is the way that the moduli space works out for a Calabi-Yau. Now, of course, if you were to study this in string theory, it would be a lot more complicated because there are a lot of background fields and things that we enter into the parameter space. So that makes it more complicated, but this is like for a base Calabi-Yau, this is what would happen. Right. So that is moduli spaces. I hope that it was as interesting as I found it. I wrote this whole section about moduli spaces because I think that this is one of the coolest parts of a Calabi-Yau, is the way that the parameter space kind of like really cleanly divides into these two parts, and that we can parameterize them using these deformations, which are isomorphic to cohomology classes. So that's it for moduli spaces. We're now going to talk about the next thing, which is the Hodge structure. But before we do that, I just wanted to quickly mention, where did I write it? It's in the previous page, isn't it? Here. So just like how delta J is a derivative of a smooth curve in MCS, similarly, we can think of, let's say that this is MK. You have that similar idea going on in the space of Kähler manifolds. So these are actually the space of Kähler classes. So we're going to call it W of T. And we can say that delta omega is equal to dw of t dt at t equals 0, where w of 0 is equal to our current Kähler class, which is the cohomology class that contains the Kähler form. So just wanted to add that in. I think in a previous recording I had that as part of the explanation, but then I forgot to mention it the second time. But yeah, if you wanted to know, these are both that. So they're tangent vectors in this manifold of the moduli space. So, okay, let's go back to what we were talking about. I'm going to skip right past to page 13, and we can get back into what we were doing. So let's call this enhanced Hodge structure. I kind of flip-flop between calling it special Hodge structure and enhanced Hodge structure. The bottom line is that this is the Hodge structure that is special to Calabi-Yaus. That's on top of the Hodge structure of the Kähler manifolds. So the first thing that we're going to talk about is the fact that because we have this nowhere vanishing M form, unique holomorphic M form, what this tells us is that if you look back to lecture 8, then the Hodge numbers are actually counting how many of these global M forms we have. And so this one corresponds to HM0. And given it's unique, we only have one. So HM0 is equal to 1. Now, On top of that, we can additionally say that because of conjugate symmetry, we also get that H0m, the one with the flipped grading, will also be 1. Okay, so with that established, this is for all of them. This is including the weak Calabi-Yaus. But if you upgrade to strict Calabi-Yaus, where our holonomy group, so here our holonomy group hol m is exactly equal to SUM, what this does is that we also get this additional restriction on our Hodge numbers, where any Hodge number of the form H0Q is equal to 0 for all 0 is less than Q is less than M. And lastly, we also need to note that for any scalar manifold, we have HMM is got to be equal to 1 as well, because we always have the scalar form to the power m over m factorial. This is the Hermitian volume form. And then you can use form, and then you can use either Serre duality, or you can use the fact that there's only one holomorphic function that's holomorphic everywhere, that is a constant function. But either way, you find that H00 is also equal to, let's not put that in the superscript, is also equal to 1. So now let's draw the Hodge diamond for this whole setup. If I can remember how it goes, H00, the P grade increases in this direction and the Q grade increases in that direction. So we get H10 and then we get H01. You can also think of it, how do I add up to get every integer at every level? So here it's 2, H20, then we get H11, and then we get H20. And then we start again, H30, H21, H22, and H03. Then we have the 4s, so H31, H22, and then H13. And then we have the 5s, H32 and H23. And then we have H33. For any Calabi-Yau, we'll always have that H33 is equal to 1, and we'll have H00 equal to 1 by Serre duality. And then we know from this property here that this will be 1, and by conjugate symmetry, this will be 1. So this is all we get so far for a weak Calabi-Yau, but then for a strong Calabi-Yau, we have some additional parameters. Remember, these are all equal to 0, and what that means is that these are 0, which conjugates over to the other side, which gives us that these are 0. Whichever way you want to think about it, you could say that H0Q is 0 or HQ0 is 0. Anyway, they're equivalent because of conjugate symmetry. So, and then we can use Serre duality to flip them onto the other side. So, I mean, this is a good place to mention that conjugate symmetry is a symmetry about this axis. So this is conjugate symmetry. Maybe I did mention this last time, but it's always nice to mention it again. And Serre duality is Serre. I don't know if it's Serre or Serre, but yeah, Serre symmetry or Serre duality will give us a flip along this side. So then we get that these are 0 and that these are 0. Pretty heavily constrained, don't you think? For a Calabi-Yau has very few Hodge numbers, and you might think, oh, we still have 4 of them left for so this is for a Calabi-Yau threefold, is what I did this for. And that's for a very specific reason. It's because we're going to be talking about Calabi-Yau threefolds in a little bit extensively. We are going to derive something for them here too. We know that these two have to be linked together, and we know that these two have to be linked together by these same symmetries. In fact, let me put that in the same colors. So these two have to be linked by Serre duality, and let me get that yellow. These two have to be linked by conjugate symmetry. So in fact, a Calabi-Yau threefold only has 2 independent Hodge numbers, H11 and H21. H11 is equal to H22, and H21 is equal to H12. So these ones are the ones that in fact enumerate the Kähler moduli. Kähler moduli. Remember we said that H11 is what would count the Kähler moduli, and H22 is just going to be equal to H21. So by extension, it would also count the Kähler moduli. H21 is, we're on a threefold right now, right? So since we're on a threefold or a three-dimensional manifold, m minus 1 will give us 3 minus 1 is equal to 2. I don't think I need to do that math for you right now, but that would give us H21, which means that this is the one that gives us the complex structure moduli. Right? And similarly, H12 would also give us the complex structure moduli. So that's it for a threefold. This is the special hot structure that we have on Calabi-Yaus. Of course, I could have just shown you this diagram. It's very symmetric, it's very pretty. But at the end of the day, it's much more interesting why these are 0, why those are 1, why it has all these symmetries. That's what we really want to know. So this is the enhanced Hod structure of the Calabi-Yau. And now we've basically covered everything that I had planned for talking about the properties of Calabi-Yaus. Now we're going to finish off the whole series by talking a little bit about why Calabi-Yaus are so cool, why they're so important to string theory, and why they're so important to pure mathematics. Yeah, let's get into the last section of the last video for this lecture series. Right, so let's move on to the next page, give ourselves some space here. And the next thing we're going to be talking about is Calabi-Yaus in string theory. Now, we're going to be really a cursory here. We're not going to get into a lot of the mathematics because I really just want to motivate why Calabi-Yaus are important in string theory. No discussion of Calabi-Yaus would be complete without why they're important in string theory. So number one is we really like this thing called supersymmetry. It's a symmetry between two kinds of particles, bosons and fermions. They're defined by this property called spin, and bosons have integer spin, and fermions have half integer spin, so like half, 3 halves, and so forth. So I'm just going to call that z plus half. So supersymmetry is a symmetry that exchanges bosons and fermions, and we like it for a few reasons. Number one, it seems to be a physically unique extension. There were some physicists who worked out some theorems to find out this uniqueness, but it's a physically unique extension of the Poincare group, which is the symmetry group that we currently have for our particle physics. Number two, it provides a mechanism for generation of fermions. Naive string theory only produces bosons, so this symmetry actually provides a way to generate fermions in addition, and obviously we observe fermions in real life like the electron, so we obviously need a way to generate these fermions. Number three, it makes a lot of problems, a lot of equations either solvable or tractable to do. Which there are a lot of decisions in string theory that boil down to this will make it possible for us to solve this equation, therefore we probably need it. Now, so with string theory, we have this thing called compactification. The really short idea of what compactification is that for internal consistency reasons, space-time has to be 10-dimensional in string theory. This is non-negotiable for versions of string theory that include fermions, and we only observe 4, right? So where is the last 6 dimensions? Well, we can wrap it up in a complex manifold that is 3-dimensional, 3D complex manifold, and it should be a compact manifold. Basically what we're doing is we're stuffing that manifold in such a small space that we won't see it, and that will explain why we don't see that manifold in real life. So yeah, a 3-dimensional complex manifold, and it's called compactification because in the topological sense, we're taking non-compact directions in our space and we're turning them into compact directions. So what does this have to do with supersymmetry? Well, during this process, we're taking this copy of R10 and we're taking it to R4, which is our 4D space that we see, some the physics way of saying this is R13, but it's isomorphic to R4, direct product with our manifold. Now, it's going to have to be a 3D manifold, so why does it have to be Calabi-Yau? Well, in order for supersymmetry to work out on this compactified manifold, if we are to preserve some supersymmetry, there's this one equation. I'm not going to get into where this equation comes from, but just suffice it to say that there's this equation that pops up. Delta epsilon of psi m is equal to, this is a spin connection on the manifold of epsilon plus some other terms have to be equal to 0. And so we require this term where this is a spinor valued parameter. We need this to vanish. And so this is required for us to have supersymmetry be preserved. And this is essentially translates to having a covariantly constant spinor. Now, might I remind you from our topological properties that this SUM holonomy is what creates the perfect conditions for having this covariantly constant spinor, and because of that, supersymmetry requires this to be a Calabi-Yau. So that means that what we end up with is a 3D Calabi-Yau, which physicists affectionately call a CY threefold. And that's why I've been talking about CY threefold so far. Of course, my background is in physics, so this specific Calabi-Yau is very important. And so that already tells us why we might want Calabi-Yau manifolds, but there are a few more reasons why we might want Calabi-Yau manifolds, and we're going to run through these a little bit more quickly. So there's another thing called anomaly cancellation. What is this? Well, we have classical physics, right, and quantum physics. So there, in the transition between classical and quantum physics, some symmetries do not survive. Symmetries do not survive. A symmetry that's in classical mechanics might not survive in quantum mechanics. These are called anomalous symmetries. And anomalous symmetries are bad news for physics theories. So we want there to be no anomalous symmetries. And one of the ways that anomalous symmetries can be made to vanish is by using a Calabi-Yau. And so we like Calabi-Yaus because we don't like anomalous symmetries. Number 3, moduli spaces. So we've talked a lot about moduli spaces. So what do they have to do with physics? Well, number 1, strings contain energy, or strings are made of energy. Whichever way you want to think about it, they contain energy, and so they have to deform spacetime. Deform spacetime. But technically, even though our Calabi-Yau is compacted, it's still part of the original spacetime, and so it should be deformed by the strings that you would have in string theory. And so since that is the case, we need a way to mathematically formulate the deformations of our Calabi-Yau, and that is given by Tian-Todorov theorem. It says that we have this smooth moduli space, and that locally turns into 2 different subspaces, and that makes it really nice. So that gives us a reason why we might want to use Calabi-Yaus to model our spacetime again. So, and then number 2 is that moduli spaces give us all of these free parameters that, upon compactification, might result in. So let me write it like this: moduli might lead to our 20 or so free parameters in the standard model. Right? It gives us a few knobs to turn and adjust so that upon compactification, we might be able to match them with the standard model. Number 4, so this is in addition to the free parameters that we talked about already. We could also produce the internal symmetry group. So far what we've been talking about, the Poincaré group, is the external or the space-time symmetry group of the particle physics. Particle physics also has an internal symmetry group that looks like SU3 cross SU2 cross U1, and in certain theories like heterotic E8 cross E8, under certain strict conditions, some version of this has been produced, which is a promising lead that string theory might be a theory of everything, which is what we wanted to do. Is we wanted to explain all known particles. These are also called TOEs. And it only did this while working on a Calabi-Yau, which is the important part to us. Another reason, and lastly, there's something called mirror symmetry. At least on Calabi-Yau threefolds, it's been shown that if you have a Calabi-Yau M, then you also have a Calabi-Yau M with a little wedge on the top. This is the mirrored Calabi-Yau, and it has the flipped Hodge number. So if this one has the Hodge number H11, H21, then this one has the Hodge numbers H21, H11. And this is interesting to physicists because certain problems that are impossible to solve on the regular Calabi-Yau are much easier to solve on the mirrored Calabi-Yau. And this will lead into, in the next section when we talk about the pure mathematical reasons, mirror symmetry is also interesting to mathematicians, and but I'll get into that more when we get to it. I don't want to steal too much from that section. So these are all of the reasons that I collected why string theory is so interested in Calabi-Yau manifolds. There might be more. I might not have gotten all of them, but hopefully it's pretty apparent why Calabi-Yaus pop up in string theory. But since we're doing math here, we should have also an equally sized section where we talk about Calabi-Yaus not in string theory. Of course, the title is a little bit tongue-in-cheek because, of course, in some sense, this is more important right now because we're doing pure math. But of course, we would have to talk about string theory when we talk about Calabi-Yaus. But with that out of the way, Calabi-Yaus not in string theory. And let me center that, and we'll get into the last section for today. So let's get right into the first point, Berger's classification. What is Berger's classification? It is a classification of irreducible. Remember, irreducible from before, it meant not being able to be written as a product of non-trivial manifolds. So irreducible, non-symmetric Riemannian manifolds by their holonomy group. And of course, the category for SUM is the Calabi-Yau. That tells us that in this classification, every manifold that falls under the SUM holonomy also has to have Ricci flat metrics. So moving on to the second one, number 2, we get this link between algebraic conditions and differential condition. And so Calabi-Yau's differential conditions. And this is because on Calabi-Yau's we have that link between having that trivial canonical bundle, and having a Ricci flat metric. The interesting thing about this is that we can see how the interplay between algebraic and differential conditions affects a manifold. 3, we have the a priori estimates that Yau made. I don't remember at this point if I mentioned them in the final recording that I made, but yes, so Yau made some a priori estimates of the solutions to the simpler version of that differential equation, and this has become a staple tool in nonlinear PDE theory and geometrical analysis. So this is where the work on Calabi-Yau's is becoming useful to other branches of mathematics. Number 4, this is one of the most interesting ones. This is called the minimal model program. It's this interesting research project where they are trying to classify algebraic varieties. We came upon algebraic varieties once before. For our purposes, algebraic varieties are manifolds that are described by polynomial equations exactly. And they want to classify these algebraic varieties by their birational equivalence class. What's a birational equivalence class? Well, two manifolds are birationally equivalent if they are isomorphic on an open dense subset of the manifold. So in our classification of algebraic varieties, of course, Calabi-Yau manifolds fall into them, or at least a subset of Calabi-Yau manifolds fall into them. And in fact, not only that, one of the main things that the program does, the program part of this idea, is that you take any algebraic variety and then you simplify it. The simplification is kind of the program. And upon this simplification process, it turns out that the endpoint can be classified. So the classification is by the sign of the curvature of that algebraic variety. And of course, so you could have positive curvature. So positive curvature, these are called Fano varieties. And negative curvature, so this one, the name isn't as neat. It's just called a general type varieties. And of course, the one that I neglected to mention, the one with zero curvature, as we know, Calabi-Yaus are Ricci flat, turns out to all be Calabi-Yaus. So they form this pivotal role in this classification program of algebraic varieties. And the classification has been successful in 3 dimensions and lower, and the general classification is open research. So the general proposition is a field of open research. Number 5, moduli spaces are also really important to mathematicians, and Calabi-Yaus act as a great testbed for ideas involving deformations, because as given by Tian-Todorov theorem, they have no obstructions to their deformations. That means that the infinitesimal transformations have no obstructions in becoming what I would call macroscopic deformations. And so that provides an interesting arena in testing the ideas, because it's the simplest case. It's the simplest arena where you can talk about these deformations. Once you introduce these obstructions, now all of your equations become nonlinear, and it's more difficult. And then, of course, as I said before, mirror symmetry. Whether or not Calabi-Yaus, so general Calabi-Yaus, have mirror symmetry is an open field of research. It was originally inspired by physics, but now mathematicians are also looking into whether you can impose mirror symmetry onto general Calabi-Yaus. There's an interesting conjecture in this domain called Strominger. I've never had to pronounce this aloud before. Strominger-Yau-Jaslow, or SYZ conjecture. And it proposes that there's a geometrical mechanism behind mirror symmetry, and it says that the Calabi-Yau and its mirror can be decomposed into these things called special Lagrangian tori, and the mirror is formed by dualizing these tori. But again, this is still open research. Number 7, and I think our last reason, is enumerative geometry. There was a famous curve counting problem, so that's where you get enumerative geometry from. Famous curve counting problem. The problem was, how many rational curves of degree d lie on a quintic threefold in 4D projective space, P4. This was solved by Candelas et al. The link to that paper is in the notes, by using mirror symmetry. Because a quintic threefold is actually a Calabi-Yau manifold. And so they were able to use the mirror symmetry of the Calabi-Yau to solve this problem. And this led to the development of a bunch of theories that have to do with counting geometrical objects. Gromov-Witten theory, something called quantum cohomology, and BPS state counting. So if you want to look into those more, feel free to look into that. But that all came from thinking about Calabi-Yaus. So let's go to our final page. And with the mathematical motivations, I want to say that they come in two different varieties. One being that Calabi-Yau study influencing some other topics of research and such things. And the other one, which is leading to, or Calabi-Yaus themselves have a lot of interesting structure that has been revealed through research on them. All right, so that wraps it up. These last two sections were really just kind of an informal discussion of why Calabi-Yaus are important to physics and math, which they are very important to physics and math. And we will conclude with a final recap of what we did today. So the first thing that we did today was, well, after our previous recap, is we talked about the history of Calabi-Yaus, and this was to talk about Calabi's conjecture, and we talked about the way that Yau proved Calabi's conjecture. We talked about Yau's proof. That led us into the definitions of a Calabi-Yau, which we sorted into three different tiers. We sorted them into weak, strong, and strict Calabi-Yaus. And if you remember, there were different holonomy constraints on each of the Calabi-Yaus. Number 3, we looked at topological properties. So this included restricted higher Chern numbers. It included vanishing Euler characteristic chi on odd Calabi-Yaus. And then we have Bogomolov decomposition, which was the étalé cover of a Calabi-Yau is isomorphic to the torus producted with a bunch of strict Calabi-Yaus xj producted with a bunch of hyperkähler manifolds yk. And then we had the existence, or let me write it like that, exists parallel spinners psi such that nabla s psi is equal to 0. This was because of the SUM holonomy. And lastly, we had unobstructed local moduli spaces. So then, number 4, we looked at said moduli spaces on the Calabi-Yau itself, which looked like curly M of Calabi-Yau is approximately equal to curly M of complex structure, direct product with curly M of Kähler form. Number 5, we looked at the enhanced Hodge structure, and we looked at specifically the Hodge diamond for a Calabi-Yau threefold. Then we discussed Calabi-Yaus in string theory, Calabi-Yaus in string theory, and lastly, we talked about Calabi-Yaus in pure math. And that should do it for today. That was everything that we covered in today's lecture. So with that, I'd like to conclude by saying a few final words. I hope this series was helpful to the people who've watched, especially the people who watched so far. I know it's a lot of content. It was a lot of content to make, and I hope it reduced the barriers to entry to complex differential geometry. I hope it clarified a lot of the concepts and made the subject easier to approach. I know that this series was in part motivated by my own struggles in getting into complex differential geometry, but funnily enough, it was the thing that pushed me to learn complex differential geometry myself so that I could break it down for other people. So some thanks are in order. I'd like to thank Meryl Badda Talks for hosting this platform and giving me this platform to talk about math for so many episodes. I'd like to thank Hasib sir for giving me the idea, for pushing me to do this. And there were definitely times where I was doubting myself about whether or not I could get through this whole project, but here we are. We're at the end. And I'd like to thank Walid, Tamid, and Samiha for the help in the logistics, especially during the live sessions. I kind of took over the whole thing when I started recording the lectures offline, but they're still helping me in uploading the videos. And I have to thank my friends Shujosh, Abdullah, Shitima, Umme, Mahsuda, and Fahim for their, let's say, non technical support while I took this massive undertaking of this research and writing project. I learned a lot of new things. I never recorded a YouTube video before this, so it was a very interesting experience to film this lecture series. And hopefully, I'll be writing more of these lecture series in the future. Maybe they'll be written, maybe I will film those as well. That's yet to be seen, but hopefully we'll meet again in another series in some topic in math or physics. And hopefully it won't be as difficult as Calabi-Yau's.